Hey, math people, lecture 3 of this 6-part series through analytical applications of differentiation. We're going to start with a warm-up, define what it means for an interval to be increasing or decreasing, look through some examples, and provide full justification for the AP gods that need it. What else? Then we're going to do this test called the first derivative test for Extrema. Helps you find min and maxes. We'll define it, go through some examples, and then cover the oddball cases. Remember, this video is for you, Tony, or whoever you are. So use the timestamps, pause, be patient with yourself, and let's do some math. Okay, so we got this goofy looking function here. Oh, and this meme is somewhat relevant too. I guess I'll talk about this first. So finding extrema of functions, and then we got all these functions here, and then we have Lindsay Lohan and Mean Girls here, and something's gonna happen. I wonder what. We'll cover that as time goes on, but we're looking at primarily this thing. When do we have an interval of increase? When does thing go up? And when do we have an interval of decrease? When does thing go down? So I want you to give me an interval from from -3 to -2, it does blank. And then from -2 to -1 does blank. Anyway, 3, 2, 1, I'm gonna cover what's down below now. So it's increasing on this interval here. So we're going up here, and then we're going up here, then here, and then forever after here. And decreasing is the opposite. So it's when the derivative is positive for interval of increase, and when the derivative is negative for interval of decrease. We're going to talk about what this means in a moment. So yeah, we're going to formally define intervals of increase and decrease. Here it is. So it's a function's increasing when the derivative is positive, a function's decreasing when the derivative is negative. Technically, in my glasses, the real definition is when the derivative is greater than or equal to 0 for increase, and then less than or equal to 0 for decrease, the or equal to part. Without getting too into it, the idea is that it's a member of the interval of increase. So we can see here this function is increasing the whole time, right? Because if you zoom in at 0, when the derivative is exactly equal to 0, right? This is a critical point. Immediately to its right, it went up, so it's a member of the interval of increase. Likewise, the same thing over here, it's a member of the interval of decrease. So am I saying that for x squared, both this point 0, 0 is both increasing and decreasing? No, I got a fun idea for you. This point is neither increasing nor decreasing, because no lone point can either be increasing or decreasing. What if we just looked at 0, 0, just floating on its own? Is this point increasing or decreasing? Huh? It's relative to nearby neighbors. So, yeah, that's confusing and a great conversation to have with differential calculus students. What I do is I simplify it and I just say, let's just look to see when we're greater than 0 and less than 0. But there's a technically there, and you should know that before we cover these problems. Okay, so your miles may vary. Maybe your teacher really cares about that. Maybe they don't. Let's look at this cubic. Find the interval of increase and decrease. We're setting the derivative equal to 0. And then we're thinking, is our output positive or negative in those intervals in between the zeros, in between the critical points? So I'll show you what that looks like. 3, 2, 1. So yeah, it's derivative to 0. Hopefully you did that. You end up getting positive and -2. Now, the new move is a number line. And what we do is we draw a number line and we just test values in between. So if I think about, what's a value to the left of -2? I don't know, -3, right? I tested that, it's positive. And how I tested it was I plugged it into the derivative. Anyways, what's a number in between -2 and 2? 0, I like that number. I plugged it into the derivative, I got -12. So I'm decreasing, my original function is decreasing. The derivative is negative. So the function is decreasing. Whereas in the first interval, the derivative was positive, so the function was increasing. If you're like, man, why are you talking to me that slow? You think I'm stupid? No, it just eventually when we juggle the second derivative into this, it actually gets confusing. Like it's like kind of hard to juggle all the different layers that are going on. So try to be with me now so that by the time we get to that part, you're not like, ah. So yeah, okay. And then last interval, it's positive output. I plugged in 3. So since the derivative is positive, the original function is increasing. All right. Okay, so yeah, the way we justify that is we say exactly that. Since the derivative is positive on this, sometimes I say on this interval, and then I write it in interval notation. So I just say, I take all the positive intervals and I slap them together and I say that's when we're increasing. And then I took that single decreasing interval and that's, when we're decreasing. So when the derivative is negative and when the derivative is positive. If you have a teacher that's like Anya about the, well, at exactly values, you want the or equal to. We're just being a little... I care about the big picture, right? If my logic is that if we're focused on just 2 points on a graph from -infinity to infinity, we're focused on too small of the bigger picture. That's my logic. If you have a problem with that, fight me. All right, find the intervals of increase and decrease. Yeah, okay. So the process. Take derivative, set equal to 0. Find the critical points too, by the way. So just generally the critical points, so points of non-differentiability. Create that number line, plug in numbers in between, get pluses and minuses, and then your positive outputs will correspond to increasing intervals for the original function. Same story for decreasing and negative. Okay, give it a go. 3, 2, 1. All right, taking that derivative, quotient rule, can't avoid it. Or at least I don't want to avoid it. I'm fine with doing it. Went ahead, took the quotient rule, did some algebra stuff. I set the derivative equal to 0, and I got -1 and 5. And then I said, wait a minute, there is an infinite discontinuity at 2, so I do have to consider that. I mean, consider how the graph literally doesn't exist on 2. So these are like the moments, we're always separating our number line with the critical points. All of them. And I don't... I kind of have a problem with calling this a critical point because it doesn't exist on the graph. But the asymptotes and non-differentiabilities I want you to consider as well. Because you could have changed sign in between those values. And certainly when you state the interval, you wouldn't say that you're increasing or decreasing at 2 when the graph itself doesn't exist at 2. So yeah, a little bit of work on this first one here. But I think it actually gets a little easier before it gets harder. Yeah, it doesn't exist at 2. So really just looking at the graph very clearly, we're increasing up to this value, then we're decreasing, and then we continue the decrease after the asymptote, and we're increasing again. So how can we find that algebraically? Well, I have my critical points, -1 and 5 on the number line, and then I have that 2 on the number line as well. And then I just plugged in numbers in between. So hopefully you trust my math there, but if you don't, that's fine. Plug in -2 into this expression. Plug in 0 into this expression. Plug in 3 into this expression, and just check the sign. So this is where like I give my students a 4-function calculator, because like that's not fun to just sit there and plug in numbers. But anyway, we end up getting positive outputs for the from -infinity to -1, and then from 5 to infinity. And then in between, it's negative slope in between the whole time, right? Negative slope, negative slope. But remember, we don't exist at 2 there. There's an asymptote, so we do have to hop over that within the statement here. So, little mean. Okay, the natural log was the second one. There's no critical points, but we do have an asymptote on 5. It actually, you can't plug in negative numbers, so it doesn't exist to the left of the log. This is where knowing that algebra helps. I mean, this is what the log looks like, more or less. I know it's not the same, but it's got the right idea to it. So it's really just increasing the whole time from 5 thereafter. You plug in 6, you get 1 as a slope, so it's +1. And there's no interval of decrease, so we just say none. Okay, next round, piecewise, and then a rational expression-y looking thing. 3, 2, 1. Process is still the same. Take the derivative, find the critical points off of it, look for those moments of non-differentiability, and when the derivative is equal to 0, and then those will be your values on the number line where we possibly switch signs, all that good stuff, and then plug in the values around it. So for the first one, it's a piecewise, looks scary. It's not. Take the derivative of the first piece, take the derivative of the second. we see here that if we were to plug in 1 into each of these, that's not a match, so that's actually a moment of non-differentiability. That's a corner. Then I set each equal to 0. You set the top equal to 0. Negative 3 is never equal to 0. Set the bottom equal to 0. That was just a scoot of the 2 divided by 2. That's at that 1. So it's really just 1 we're considering. So the horizontal tangent of the parabola is exactly when we switch from the parabola to the line. Anyway, we just get that 1, and I plug in a value to the left, I plug in a value to the right, negative on the left, positive on the right, so we get the corresponding interval of increase, decrease. Next one, took the derivative, used the chain rule. So I just worked off of the rational expression on the outside of the cubic here. So I brought that 1/5 up front, subtracted 1 in the power, multiplied by that chain rule. So derivative of inner is 2x. And then I rewrote it to get this expression. I see here that derivative is equal to 0 at 0 if I just set 2x equal to 0. And then down below, I have 2 vertical tangents at 1 and negative 1. So these are all my values I'm considering. Testing the values in between, I like to test like -½ and half when this happens. And then I tested -2 and 2, all into the derivative. You get negative, negative, positive, positive. So here's the thing though. You'll notice that within the last one over here, I hopped over this 2. And now you're thinking, now wait a minute, you're not hopping over that -1 and that 1. What's the deal? Well, first, okay, I can answer that in 2 ways. Just on the algebraic front, these were moments of non-differentiability, but they exist on the function itself. Within this one, it was an asymptote, so the function itself did not exist at 2. This function exists at 2. I can just 1, I guess, at 1, and in this case, 2 was the asymptote. This function exists on 1. You plug in 1, 0 is the output, no big deal. These are vertical tangents. These are vertical tangents which, continuity is preserved. So I want to do the nth root, which is the 5th root of x squared minus 1. So you can see here I got these 2 vertical tangents, and then I have, this critical point. So we're decreasing the whole time here. We're still decreasing. We're decreasing the whole time. We're still going down from a point immediately to the left of the vertical tangent to a point immediately to the right. It's just decreasing throughout this interval, and then once we get to 0, it's just increasing thereafter. So this is where having access to the graph is nice, because you can verify a few of these things. So we are including these values here because it's continuous at those values. All right, here's a fun one. So here we're looking at the derivative. So if this is in fact the derivative, so instead of working off of the algebraic derivative, what if I'm working off a graphical derivative? What can I say about the interval of increase for the original function off of this graph? If you're thinking, oh, well, I'm increasing from 0 to infinity and then decreasing from -infinity to 0. Nope. The reason why is because we're looking at f prime. So this is the derivative. The outputs here, if it's positive output, that means the original function is increasing. If it's a negative output, below the x-axis, the original function is decreasing. So use that. 3, 2, 1. Really think about it. We have all positive outputs on the left side of -2. All positive outputs on the right side of 2. So we're positive. We're increasing. The original function's increasing since the derivative is positive at these 2 intervals. And then in between -2 and 2, the original function is decreasing because the derivative is negative. All right. So, Lindsay Lohan's fallen into the garbage can now. Why? Yeah. So in terms of all these, this has a critical point at 0, critical point at 0, critical point. They all have critical points at 0. And then they actually turn out to be extrema at 0. So look at this. It's an extrema at 0. But this has a critical point at 0, the cube root of x. Alas, it is a vertical tangent though. So it doesn't have an extrema at 0. It's the only one that's garbage. I mean, we kind of saw it as such over here, right? Like this was not these were not extremas. These were vertical tangents. So anyway, extrema. Well, we want to talk about that. So we're going to use the first derivative test for Extrema right now. Here's how it goes. Suppose we have a critical point. If the derivative is positive on the left and then negative on the right, we call that a max, relative max. And then likewise, if the derivative is negative on the left and then positive on the right, we call that a relative min. If it's the same side on both, it's neither. So you end up getting exactly this scenario, like same on both sides. This is neither a min nor max. Here, opposite signs on both sides, it was a, well, let's think about it, right? If we have a negative slope on the left of one and then a positive slope on the right, it goes from negative to positive. This would be, in fact, a minimum value, right? So we're decreasing until we're increasing. And if these flip-flop, flip-flop, like right here, from positive to negative, positive to negative, positive to negative. It's a maximum. So, and then if it's the same sign on both sides, then it's neither. So vertical tangent case. Let's talk about this scenario, yeah? So take the derivative, set it equal to 0, still do the number line. Number line's good. And then just observe when the sign goes from the derivative, right? Positive to negative, that's a max. And it goes from negative to positive, it's a min. So 3, 2, 1. All right, so we got a few things going on here. I went ahead, took the derivative. I got that nice quadratic. I got 0 and 8 as the solution. So I'm going to graph the original function so we can just kind of verify all these nice things. 12x squared. Zoom out. Huh? That's really, oh. Here, I'll show you. I graphed it. I'm like, this is really what it looks like. It looks like a quadratic. Oh. All right, that's a really boring graph. Okay, so we go from a negative, we found the two critical points. I plugged in -1, I plugged in 1, and I plugged in like 10. Those are my outputs. Those are my signs. So if I'm going from a negative slope to a positive slope at 0, okay, let's think about this. Negative slope to a positive slope at 0, that must be a minimum value. That must be a min. And then likewise, looking at the other side, going from a positive slope to a negative slope. So looking at 8 now. Positive slope, what? Positive slope to a negative slope, that must be a max. Must be a max. Relative max, right? Because we do go higher over here and then we go lower over here. This only helps us with relative extrema. If you want absolute extrema, you want extreme value theorem, which is the last lecture. Anyway, so yeah, we just say that f of x has a relative min. Where's my cursor? Hello. Relative min at 0 because that value, at that value, f prime switches from negative to positive. This is like the full AP justification. Sometimes people write like inequalities here with the derivative, but this is just fine. Positive to negative, negative to positive, all that stuff. Okay, let's just practice doing it. So just find the relative extrema, relative mins and relative maxes. Hopefully the polynomial case ain't too bad. This one, you got a non-differentiability, hint, hint. So 3, 2, 1. Here we go. You set the derivative equal to 0. You found those moments, and you're looking for those sign flips. So it goes negative to positive, and then positive to negative, and then negative to positive again. So we have 2 mins and 1 max. Looking at 9, we have that non-differentiability at 6, right? That's when we switch negative to positive. You know, that's where we got that little v. So I just know 6 is the value. And ultimately, I'm just plugging in any number like 0. That's to the left of 6 on the left side here, and then to the right of 6, 10, whatever, comes out to a negative number. Here's the thing: if you just knew your transformations, parent transformations on just the absolute value, so like if you really think about this, what this is it's flipped upside down, yoink, it's scooted 6 units to the right, yoop. These are all the noises. And then it's 3 units up. Plus 3. This is just literally what the graph is. So, we're going up, then going down. So this is where we hope you know algebra. We hope. Is that true? Different story. All right. Round 2 or whatever. 3, 2, 1. Yeah, so same story here in terms of The fact that we're just using chain rule again, I feel like we saw an e to the something earlier. Hopefully that was this lecture. But anyway, yeah, it's just chain rule. So e to the blah is e to the blah. And then derivative of inner is this 2x plus 6. This is never 0. This can be 0. It's at -3. So you just find an output to the left and then an output to the right. We go from decreasing to increasing. So that's a relative min. Then over here, this one, it's the cube root. We talked about this. This is that Lindsay Lohan case. For some reason, I'm attributing her to that. Yeah. So this is neither a min nor a max because we go positive slope to positive slope. So no relative extrema. All right, another round. 3, 2, 1. Fourth power is good. So really, it's just like particular cases with powers. So like this was the cube root, so like the 5th root or 7th root that's going to create those vertical tangents. So noticing patterns within the powers is really something worth talking about. Because if you think about x cubed, right? Odd here. It's just increasing to increasing. This is even, and I'll bring that to the 4th power, and decreasing to increasing. So decreasing to increasing, or negative to positive with the derivative. That's a relative min. And then this one's kind of goofy. I did quotient rule. I saw the asymptote at 0. Careful for that. So I found a critical point at -2. I consider the asymptote at 0, and I go negative, positive, negative. Just be mindful, it didn't exist at 0 if it's an asymptote there. It's an infinite discontinuity. Just because we go positive to negative here doesn't mean, oh, okay, it's got to have a relative max at 0. Not quite, because it doesn't exist at 0. But it does exist at -2, which is a relative min. Okay, is this the last case? Oh, no. All right, some graphical scenarios. Hopefully didn't pause at any of those. Given f prime here to the right, find the relative extrema of f. Okay, so this is the derivative. Do not tell me that this is the max and this is the min, because I'm asking about f and I'm giving you f prime. So think about the sign switches. When does the output go from negative to positive and vice versa? 3, 2, 1. Yeah, so take a look here. We go from negative to positive at 1, so decreasing to increasing, that's a min. And then we go from positive to negative at 2, that's a max. And then we do the same thing at 4. I don't know why I wrote 3s here. I think I just wanted a 1, 2, 3, but I put it at 4. So then we have a relative min at 4. This is 4. This is 4, 4, 4. This is 4 for 4 for 4, 4. Yeah. Anyway, so yeah, we're going from negative output to a positive output at 4. So negative to positive, that's a minimum value. For the original function, which we don't have access to, we're just looking at the graph of the derivative, which is just some information for f. Okay, so those 3 should be 4s. All right, looking at 15. All right, this is f prime again. So given that the fact that this is f prime, help me find the interval of increase, decrease, and then all of its relative extrema. This is f prime. Do not tell me that this is a relative min, this is relative max. No, this is relative min, no. This is f prime. So always know what derivative you're looking at. 3, 2, 1. To end the day here, we go from positive to negative at -7. So that would be your maximum. We see here the sign at -1, we go from negative to negative, right? We don't breach through, so that is neither a min nor a max. At 2, we go from negative to positive, so that would be your maximum. And then we go from positive to negative at 8, that would be your, what? So for 2, we go from negative to positive, that's a minimum, there we go. And then at 8, we go from positive to negative. Sometimes I have to do that. Like, if you need like a little trick, like just like to like, I sometimes see students do that when they're taking this test. I see them go like that, and then think about it like as a drawing. So, you know, lean into the intuition and the, you know, just the general matter of fact, the big picture. Don't lean too heavily on just the process. Anyways, we go from positive to negative. That would be at 8, so that would be a maximum there. So working off that, we get our intervals of increase and decrease as well. Okay, that's it for today. Math on.